Asking about the shape of the universe is more complicated than it sounds. We're used to thinking in terms of familiar three-dimensional objects, spheres, cubes, flat planes, but the universe is a vast, dynamic structure governed by the laws of general relativity. Its shape isn't something we can simply walk around and see. Instead, we infer it from measurements, observations, and theory. In modern cosmology, there are three main possibilities for the large-scale shape of the universe. The first is a flat universe, which follows the rules of Euclidean geometry, the same geometry you learned in school. In a flat universe, parallel lines stay parallel forever, and the angles of a triangle always add up to exactly 180 degrees. A flat geometry can extend infinitely in all directions, and it has no global curvature. This is the model most strongly supported by current observations. The second option is a closed universe, which has a positive curvature, like the surface of a sphere. In this kind of universe, space curves back on itself. If you traveled far enough in one direction, you could, in theory, end up back where you started, just as you would if you kept walking in a straight line on the surface of Earth. A closed universe is finite in volume but doesn't have an edge or a boundary. The third possibility is an open universe, which has negative curvature, similar to a saddle shape. In this model, parallel lines eventually diverge, and the geometry expands infinitely without looping back on itself. The way scientists determine which model fits our reality is through careful measurement, particularly of the cosmic microwave background radiation, the faint afterglow of the Big Bang. The patterns in this radiation act as a kind of cosmic blueprint, revealing how space is curved on the largest scales. So, what's the shape of the universe? The results from missions like the Planck satellite show that, within a very small margin of error, our universe appears to be flat. That doesn't necessarily mean it's infinite. It could be incredibly large and still wrap back on itself in ways we can't yet detect, but it does mean that space follows Euclidean rules across the observable cosmos. It's also important to remember that these models describe the universe's large-scale geometry, not the shapes of local objects or structures. Galaxies, clusters, and filaments of matter can form complex patterns, but on scales of hundreds of millions of light-years, the universe smooths out into one of these broad geometric forms. The best evidence we have today points to a cosmos that is remarkably flat on the largest scales we can measure. But the question is far from settled. With better instruments and more precise data, we may one day discover subtle curvature, or even find that our universe connects back on itself in ways we can't yet imagine. Why flat doesn't mean what you think. When cosmologists say the universe is flat, it's easy to picture something like a sheet of paper, or maybe a cube with flat faces. But that's not what flat means in this context at all. In fact, the term refers to the geometry of space, not its physical appearance. If the universe were positively curved, like the surface of a sphere, those rules would change. Parallel lines would eventually converge, and the angles in a triangle would add up to more than 180 degrees. If the universe were negatively curved, like a saddle, parallel lines would diverge, and the triangle's angles would add up to less than 180 degrees. What makes this tricky is that we're talking about three-dimensional space rather than a two-dimensional surface. A flat universe in 3D isn't thin, and it certainly isn't limited to two dimensions. It can extend infinitely in all directions while maintaining zero curvature. You can't see its flatness just by looking around. Instead, scientists detect it by measuring how light travels over vast distances and how matter is distributed on the largest scales. Here's another point that can be confusing. a flat universe could still be finite. Just as the surface of a cylinder can be flat in one direction but wrap around in another, it's possible for our universe to be both geometrically flat and topologically connected in a way that loops back on itself. That would mean traveling far enough in one direction could, in theory, bring you back to where you started, without requiring any curvature in the local geometry. Observations from the cosmic microwave background give us strong evidence that space is very close to perfectly flat. But close to flat isn't exactly the same as flat, and even tiny deviations could become meaningful over cosmic distances. That's one reason why cosmologists are still refining measurements, looking for any sign of curvature. So, when you hear that the universe is flat, think about geometry, not shape. It means space behaves according to the rules of Euclid, without large-scale bending toward or away from itself. It doesn't mean the universe is two-dimensional, and it doesn't mean it looks like a disk floating in space. It means the cosmos, as far as we can measure, is a vast expanse with no detectable curvature, at least, not yet.